2022. Alrighty, here we are. Question 13.11b comes from our textbook. And I think first we're going to name this compound as an oxirane. So if we want to name it as an oxirane, we're going to focus on the three-membered ring. And keep in mind that when you're numbering an oxirane, the oxygen is always going to be number one, right? An oxygen has a higher atomic number than carbon. So we have our number one here, and then we have two carbons attached to that oxygen. Well, this carbon is the only one with substituents on it, and we want to give those substituents the lowest possible number. So we have 1, 2, 3, like that. So we have two phenols at carbon number 2. So we have 2,2-diphenyl oxirane. We'll scribble that down, 2,2-diphenyl oxirane. All right, so that's done. I'm going to erase those numbers so we don't get confused, because now we're going to name it as an epoxy compound, as an epoxide. And so what we do now is we look for the longest carbon chain that contains the epoxide. And the longest carbon chain is these two carbons, just two carbons. So we can either number them 1, 2 or 1, 2. Well, which way is it? If I number it the way that I have right here, where the number 1 is on the geminal diphenyl, well, then it's going to give the diphenols a lower number, because either way you'd get 1, 2 epoxy, you'd get epoxy ethane. And I guess you don't need to give a locate to the epoxy ethane because there's only two carbons in ethane anyway. So this compound would just be 1,1-diphenyl epoxy ethane. So we'll scribble that down, 1,1-diphenyl epoxy ethane. And if you didn't follow me on what I said about the whole why don't you have to call this epoxy ethane, is because there's only two carbons anyway. So if you called it 1, 2 epoxy ethane, the 1, 2 is redundant, so there's no need to put it in there. All right, there we go. So those are the names of this compound. We named it as an oxirane and as an epoxide. Let's try this one. This one's a little tougher. We got a couple of stereocenters in here. Why don't we try naming it as an oxirane first? And this one's a really interesting example. Okay, so if we want to number the three-membered ring, we're going to start with number 1 on the oxygen. But this carbon is attached to a carbon, and this carbon is attached to a carbon. So which one is number 1? Or sorry, which one is 2 and which one is 3? Well, we look at what they're attached to. So they're both attached to the same things. So then you have to move out past that, and you see that this carbon is attached to a carbon, which has two carbons attached to it, whereas this one is attached to a carbon with only hydrogens. And therefore, the isopropyl group is going to take precedence over an ethyl group. And so we have 1, 2, 3. So now we have a 2 isopropyl and a 3 methyl oxirane. And now we need to figure out what the stereochemistry is at the two stereocenters. But first, let's write down what we've got. So we've got 2 isopropyl, 3 methyl oxirane. Actually, I think I gave you the wrong rationale for why the isopropyl is 2 and the methyl is 3. It would actually be based on alphabetical order, wouldn't it? Right, because isopropyl comes before methyl. So that would be the correct one, right? Because you're thinking about this chain, and you have 2 carbon-based groups on each carbon, so you go by alphabetical order. All right, so I fixed that. Now let's take a look at the two stereocenters. So we'll start with the stereocenter on the right-hand side where the isopropyl is, because we're going to have a 2 something, and then 3 something, and then 2 isopropyl, yada, yada. All right, so let's figure out what the stereochemistry is at carbon number 2. So let's see here. We've got a hydrogen going in the back. That's going to be our lowest priority. We have the oxygen up here, which is highest priority. This carbon is second. This carbon is third. So we're going from 1 to 2 to 3, which is S. So that means that the compound is 2S. Let's erase all this scribble, and let's look at the other stereocenter. For the other one, we have the hydrogen going in back. It's going to be group number 4. This will be group number 1. This would be number 2, and this would be number 3. So now we're going from 1 to 2 to 3. We're going clockwise. which is R, so it's 2S, 3R for these two stereocenters. So let's erase all that spinach. And there we go. So now we've figured out the entire name of the compound as an oxirane, 2S, 3R, 2-isopropyl, 3-methyl oxirane. Now let's name it as an epoxy compound or as an epoxide. So the first thing we do is we find the longest carbon chain that contains the epoxide. So that's this chain here. We want to give the epoxide the lowest possible numbers for the locants. So 1, 2, 3, 4, 5. So that means we've got a 2,3 epoxy 4-methyl pentane. So we can scribble that down. 2,3 epoxy 4-methyl pentane. And now you have carbons 2 and 3, which have stereocenters. We've already determined the stereochemical configuration at both of those stereocenters. But if you remember before, this was carbon 2 and this one was carbon 3 in the first example. Now they've switched. So that means that this compound would be 2R3S. 2R3S, 2,3S, 2,3 epoxy 4-methyl pentane. And there you have it, my friends. I named both of those compounds. It wasn't easy, but we did it. All right, well, let's move on now that we've covered nomenclature, and let's try some practice problems. So here we go. We're taking cyclohexyl bromide. So this is question 13.24a, and we're trying to make this alcohol. And all we need to do is provide some reagents. Nothing more than provide some reagents. But as you know, these kind of questions can be challenging. But I think, Emily, it's the best way to master the content. You know, it's the best way to really get into this stuff and make sure that you understand what is really going on. Now, something that I want you to remember from this chapter is when you see two carbons, when you're adding two carbons and then a hydroxyl, we can think of using oxirane as an electrophile. Well, cyclohexyl bromide isn't a nucleophile, is it? However, we can convert it into a nucleophile if we convert it into a Grignard reagent. So we would treat it with magnesium. You can put a solvent, you can leave the solvent out. Either way, I don't care, but we usually use diethyl ether as the solvent, and that will give you cyclohexyl magnesium bromide, or the cyclohexyl Grignard. I'm going to draw it as a carbanion because that's the way I like to do it. Helps me think of my mechanism. Now, if we're using oxirane, I mean, it's a symmetrical molecule, so the nucleophile is only going to attack, one place. So we would use our oxirane like this, and our nucleophile is going to attack. There's no regioselectivity to worry about in this case. And we're going to open up that epoxide, and we're going to end up with this compound where we've added 2 carbons, and then we have an alkoxide hanging off the end. So to protonate that, you could use H3O+, you could use H2O. We'll just put H2O or H3O+. Either one is perfectly fine with me. All right. Let's see here. Another problem. Sorry, I'm having a technical difficulty here with my computer. Just bear with me 1 second. There we go. All right. Is everybody with me on that one? I think that one's okay. It's certainly not easy, but I think it's a reasonable job. Okay, cool. Thanks, Emily. Good. Let's try another one. Let's try one that involves another epoxide. So this is 13.24C. So 13.24C. You're starting it with cyclohexyl bromide again. Bromocyclohexane, either way, same thing. And then you're making this compound. Now this one, regioselectivity comes into play. So now we're not adding just 2 carbons, we're adding a total of 4 carbons to make this compound. So what would our path look like to make this compound? Could anybody tell me what the electrophile would be in this reaction? Could anybody name the electrophile one we've looked at already. You can either unmute your mic or type it in the chat. How would you name the three-membered ring that we would need to make this compound, this final product? Even if you can't name it and only describe it, that's good enough for me. Could anybody provide a name for that electrophile? Yeah, it's an epoxide. Absolutely, Nick. Absolutely. Well, what would we have on that epoxide? That's what we need to figure out. Okay, so let me show you again Mr. Dion's kind of retrosynthetic way of doing this. Whenever you add two carbons and then a hydroxyl, what I like to do is draw the lone pairs in on the oxygen, like this, and then I say, well, the three-membered ring came from, it's like, kind of like, and this is kind of like a backwards mechanism. Okay, this is just something I'm kind of making up here. But what would happen if you drew those arrows in reverse, right? You would end up with this epoxide. You'd end up with something that looks like this. Of course, it would have a hydrogen on it and a positive charge. We'll just ignore that for now because this isn't an acid catalyzed. It's not going to be an acid catalyzed ring opening. But you'd have to start with this compound, which is 2,2-dimethyl oxirane. Exactly. Thanks, Caitlin. Perfect. You guys are both on exactly the right track, okay? I cannot argue with any of your ideas. They're both good. So what we're going to do is we're going to make our green yard using magnesium and diethyl ether. Same thing we did the last problem. We end up making cyclohexyl magnesium bromide, our green yard. Now we're going to treat it with our 2,2-dimethyl epoxide, or oxirane, 2,2-dimethyl oxirane. And our nucleophile is going to attack the least hindered carbon. So that means it's going to attack this carbon. It's going to open up that ring, which is going to give us 1, 2 carbons, our oxygen, which is going to have a negative charge on it. And then we've got the 2 methyls coming off of the second carbon. Look, you've got carbon. I'm going to number them not according to nomenclature, just according to the problem. So we've got 1 and 2. So look, this is 1, this is 2. And you can see that attached to 2, there's 2 methyl groups directly on there. So now what we need to do in the last step is just treat that with mild aqueous acid. So we'll just put H3O plus and we're done ski, just like that. All right, let's try something else. Let's try, I got a whole bunch of different problems here. Let's try another one. Try another synthesis problem. What if we do something like this? So this is D, so 13.24D. If we start with bromocyclohexane, the author's favorite compound, I guess, in this chapter. They must have had a fire sale on bromocyclohexane or something. And if you want to make a ketone, okay, and we're adding a whole holy host of carbons here, well, you can see that you wouldn't use an epoxide to make this compound because you have 1 carbon where you have your oxygen. The only time you think about using an epoxide is when you have 2 carbons followed by an oxygen. So that means this would not be our, excuse me, we would not be using an epoxide here. However, if we think in terms of retrosynthesis, you know, what if we had this aldehyde? If we had that aldehyde and we made a green yard the same way we did before, so if we made this same old green yard, then the green yard could attack over here and we would end up with a secondary alcohol, but we could oxidize that using chromium trioxide or PCC or Des-Martin periodinane or the Swern oxidation, any one of those methods that we used. And that's really the most difficult part of this problem, in my opinion, is knowing that you need to have this aldehyde. So you can assume that if you need a little aldehyde, a small aldehyde, that you have that at your disposal. So we take our green yard, we treat it with this aldehyde. So here's our aldehyde, and we'll do aldehyde nomenclature later on in this class, which is just going to attack that carbonyl. That's going to give us the alkoxide. maybe I'll do both steps. So 1, 2, and in the second step, you treat it with H3O plus. And so that will give you this alcohol. And then if we want to oxidize that, you can use PCC or Des-Martin periodinane in dichloromethane, or you could use a SWERN, which is what? Oxalyl chloride and DMSO in the first step, and then you have triethylamine in the second step. Any one of those would work, or you could use sodium dichromate. Any one of those reagents will work to perform this oxidation. Any questions about that one? And again, never hesitate to ask me a question. You're never bothering me. If you want to stop me anytime and ask me a question. All right, is everybody with me on that one? I guess so. Let's try. Here's an interesting one. Let's try this synthesis problem. So this is, I think it's 13.51a. This is when we're going to take 1-butene, and then we're going to convert that. So 3-pentanol is kind of an interesting problem, this one. Really got to have your thinking cap on to solve this one, because we're only adding 1 carbon, right? We have 1, 2, 3, 4 carbons. Here we have 1, 2, 3, 4, 5. And then we have a hydroxyl in the middle. So we only need to add 1 carbon on the molecule. And somehow we've got to put a hydroxyl group at this position. Now, how would we do that? Does anybody have an idea where you might start with this one? This one's kind of different than the other ones because now we need to make the electrophile and then we'll add the nucleophile as a reagent, as opposed to what we did in the last 2 problems. Yeah, Caitlin, it definitely involves a green yard, doesn't it? Absolutely. Well, one thing that I notice here is kind of like, you notice that you kind of have like the 1, 2, and then a hydroxyl kind of thing. I mean, you could do it on this side too. You could say 1, 2, and then you've got a hydroxyl group here. So if you did a backwards mechanism here, and this is something, again, I like to try it a lot of times, and this is just something that I do, which says, how shows how weird I am. You do a backwards mechanism like this, then what you would need to start with would be this, where you have an epoxide here. Of course, it would end up with a hydrogen, but let's just forget about that. And then, this is the less hindered carbon. So if you treated that with methyl magnesium bromide, the methyl is going to attack the least hindered carbon and open it up, and that would give you the final product. So then the question becomes, well, how do I go from 1-butene to this compound, which is 2-ethyl oxirane? How do I make that? Well, all I need to do is to treat that with MCPBA, because that will do an epoxidation. So we take it and we treat it with MCPBA. That gives us our epoxide. And now we can treat it with methyl magnesium bromide, so CH3 minus MgBr plus. That's our nucleophile. It's going to attack at the least hindered carbon. It's going to open up the ring. And then we end up with 1, 2, 3, 4, 5 carbons. Then we have our alkoxide in the middle. And now all we have to do is treat that with H3O plus or water, and you're done. Very interesting problem. Very cool problem. Not an easy problem, but definitely doable. Definitely a manageable problem. Let's see here. Let's try another one in a similar vein. So this is question 13.51D. 13.51D. And now it's this really deceptively simple problem. You want to take 1 chloropropane, then you want to make 1, 2, 3, 4, 5, 6, and you want to have a chlorine here. Okay, you want to put a chlorine, and you're adding a total of 3 carbons here. Adding a whole bunch of carbons. So what have we got in terms of ideas? Does anybody have an idea about this one, how we might do this? what if we do a retrosynthesis? And one of the reactions that we learned was how to take a secondary alcohol and to convert it into an alkyl chloride by using thionyl chloride, so using SOCl2. SOCl2 and pyridine, of course. Anyhow, so if we could make the alcohol, right, and then you could do a second retrosynthesis where if you kind of did that backwards mechanism thing and you went like this, okay, you'd end up with something that looks like this, where you'd have, a Grignard reagent like this, but then you'd have this as your epoxide. Could we make a Grignard from this? Yes. Can we assume that we have a 2-methyloxyrene? Yes. Also yes. And so there's our retrosynthesis. Now we've kind of solved the entire problem, really. And so all we need to do is first convert the 1-chloropropane into a Grignard using magnesium and diethyl ether. And that's going to give us propyl magnesium chloride. You can draw it like this. There's no problem drawing it that way. However, I like to leave out this bond and I like to put in the negative charge and the positive charge. It's easier in terms of drawing the mechanism, in my opinion. So now we're going to take that Grignard and we're going to add this electrophile to it. Again, the nucleophile is going to add the less hindered carbon. It's going to pop that ring open in the first step, and then we're going to treat that with aqueous acid, which is going to make the alcohol. So we have 1, 2, 3. Let's count them. So this would be 4, 5, and 6. So 4, 5, 6. And on the 5th carbon, that's where the hydroxyl will be. Now, to convert that to the alkyl chloride, all I have to do is treat it with SOCl2 and pyridine, and I'm done. Done like dinner. Okay, let's try maybe an acid catalyzed ring opening reaction. Let's see here. Yeah. Let's try this one here. Yes. Let's try one that involves an acid catalyzed ring opening. So this is question, I think it's question R. I think it's 13.51R. 13.51R. Now we're going to take cyclohexanol and we want to convert that into this compound where we've got 2 functional groups. We've got the ether, then we have 1, 2 carbons and a hydroxyl. We want to have the geminal dimethyl here on this carbon. So what are the reagents that we would use to do this reaction? Well, it's not going to involve a Grignard with an alcohol. The bond that we're forming is this bond right here. So how would I do that? I mean, you could try to do the reverse mechanism thing that I showed you, where you put in the lone pairs on the oxygen and then you just draw a backwards arrow. So you say, okay, if I broke the bonds here like this, and again, this is just the thing that I do. David Klein didn't invent this. Mr. Dion did. And they're improper arrows. So, but that means you'd have this, and then you'd have 1, 2, 3, and then you'd have a gem dimethyl like this. Okay, just ignore the proton. So how would you get these things to react with one another? Well, if we had this alcohol, this alcohol is not a strong nucleophile, but if we treated this oxirane or this epoxide with acid, then we would make the oxonium. And then if you look at the carbon where I'm putting the blue delta plus, it's going to be a weaker electrophile than the carbon with the black delta plus. This is where the nucleophilic attack would occur, right? Because we have a primary carbon, and then we have a tertiary. And we know that if we use acid catalyzed ring opening, the nucleophile is going to attack preferentially at the tertiary position. And so that would be the type of reaction conditions that we would have to use. We would have to use an acid catalyzed ring opening. Therefore, our reagents are going to be nothing more than taking the alcohol and treating it with the oxirane. So in this case, it'd be 2,2-dimethyloxirane and H3O plus. And that's it. That's the only reagents you need to do this reaction. Nothing else at all. Excuse me. Let's see here. Are there any sorry, go ahead.
So if you do the ring opening with the strong nucleophile, then does it always attack the least substituted position?
Yes, always.
Okay.
100% of the time. So let's say you took, just for example, let's say you took that same epoxide and you treated it with methyl Grignard. So just CH3 minus MgBr plus. It's always 100% of the time going to attack the least hindered position. It's only when you protonate this thing, if you protonate this, in that case, it's a specific case, you have a tertiary substituted carbon and a primary, and the nucleophile, which in this case is a hydroxyl, which is not a strong nucleophile, is going to attack at the tertiary position. It's counterintuitive, isn't it? But the reason it does that is because this bond is weakened by the fact that that carbon is tertiary and it can take on more of a partial positive charge than the other one can. Does that help a little bit?
Yeah, that makes sense. Thank you.
Yeah. And again, hey, Caitlin, don't hesitate to ask me anything. I like answering questions. And I don't know if you remember, but what's today? Wednesday. On Monday, when we first started this chapter, the first thing I told you when we were on the introduction slide is that it's not easy for students to remember, if you have an epoxide, okay, and if you treat that with any kind of strong nucleophile, like some of the examples that they gave you were a thiolate like this. The thiolate is a strong nucleophile. It's going to attack like sugar. Let me just make that same old epoxide, right? The thiolate, it's going to attack at the least hindered carbon, okay? And then that would give you, after workup, of course, so you have to do another step, you have to do the aqueous workup, but that would give you, this compound where you have the hydroxyl here, you have the CHEM dimethyl, and then you formed a sulfide like that. Okay, let's try another one. Let's imagine you had, I don't know, cyanide, right? That was another kind of a dark horse, one we don't look at a lot. But let's say you had sodium cyanide. Well, cyanide is a strong enough nucleophile that it's going to attack at the least hindered carbon, right? And then after workup, that would give you the same thing, where you'd have the hydroxyl here, the CHEM dimethyl, and then it becomes a nitrile. And another funny example, it's not funny, it's just an example we don't see a whole heck of a lot. The other example that they gave you was a hydride. Like let's say you used LAH and you had lithium aluminum hydride. Again, one that doesn't show up a ton, but it can happen, right? That serves as a hydride delivery agent and it attacks the least hindered carbon so that you would end up with same thing after protonation. You end up with just this compound. So you'd end up with tert-butanol in this case. The difference, is really when you have an acid catalyzed ring opening, if you have a primary carbon and a tertiary carbon, okay, and you treat that with H3O plus a weak nucleophile like an alcohol, okay, so once this gets protonated, so I'm just going to kind of skip the entire mechanism and draw part of it. The weak nucleophile is going to attack the tertiary carbon. However, look, I'll even copy and paste this. Look, copy it. So copy it, and I'll paste it down here. So come on, you, paste. There we go. Worked perfectly, right? Son of a gun. Anyhow, so if we have a primary and a secondary, so let me just erase another one of those bonds. So you have a primary and a secondary. In that case, it's going to attack the least hindered carbon. Okay, so now our alcohol is going to attack the least hindered carbon. So whenever you have a tertiary, it's always going to go for it. But if you have no tertiary, it's going to go for the least hindered carbon. So it's that tertiary that's kind of like an exception in a way. Does that make some sense?
Yeah, that makes sense.
Yeah, just a little bit of review, right? And I told you, it's tough to separate those things. I remember the first time I taught this, something I learned a long time ago, but you start to forget, all the different rationales and everything. So yeah, that's kind of the summary of the two different types. So this is just nucleophilic attack. This is nucleophilic ring opening. And then this one here, what I'm looking at with both of these, this is acid catalyzed ring opening. So just a little bit different. Something else that I think we should talk about is why don't we try a ether synthesis problem? I mean, we made one ether in the last problem. Let's try another one. Let's try this. What if you took like 1-butene, okay? If you took 1-butene and you wanted to make this, so let's just put an ethyl group over here. How would you do that? Could I give you a minute or two to think about that? I'm not going to turn off the recorder or anything, but I'm just going to go grab a drink of water. I just finished my coffee, so I'll be back in like 60 seconds or something. Anybody have an idea about this one? Making an ether and adding 2 carbons? A couple of ways you could do this, I suppose. A couple of ways off the top of my head.
Could you start by the anti-Markovnikov addition of water, and then you need to do the Williamson ether synthesis?
That's what I like the most. I'm with you, Caitlin. This is the first thing that came into my head is to do that. So what Caitlin is saying is just do an anti-Markovnikov addition of water, this old chestnut, so borane and THF, followed by peroxide and base. And that's going to give us 1-butanol. And then she said, well, Williamson ether is nice chemistry. First step, you just treat it with a base like sodium hydride. You make the alkoxide. You could use sodium too, I suppose. But sodium hydride's a better base because it makes hydrogen. Well, I guess the other one makes hydrogen too, does it? Anyhow, sodium hydride. And then in the second step, she'd treat it with, ethyl iodide. Okay? And this, again, this is the Williamson ether synthesis. Right, great reaction, great chemistry. I think this is a beautiful way of doing this problem. I think this is 13.51G, 13.51G. I think there's another way to do it, though. Did anybody come up with a different way? Might not be as pretty as this one. But there is a way that would give you, and it might not be as high yielding, actually. You might get some, a little bit of elimination. But another way to try this one, and this is, I would accept this. I don't think it's as good as this synthesis. This is, I would give this 100%. Okay, so if you took this, what if you tried to do just an anti-Markovnikov addition of HBr? Use HBr and peroxides, so that you end up with this. And then what if you just treated that with sodium ethoxide? Sodium ethoxide. All right, that's just going to do an SN2 like that, and that would give you the product as well. The only thing is that, this is SN2, but you'd also get a little bit of E2 here. So maybe not as good, but hey, it's okay. It's all right. I'd still give it full points. Let's try, hey, I like this one. Let's try this problem. Another neat one from our textbook. This one is where you take this compound. This compound, you could call it methoxy benzene. There's nothing wrong with that. Or it's also got a common name, which is anisole, named after Jennifer Anisole from the Friends show. Anyhow, so you take anisole and then you can convert it to ethoxy benzene. All right, could anybody figure that one out? Kind of a weird problem, but I like it. I really like this problem. Let me just move it down here a little bit. So how would we do this? You know, I mean, if you had phenol, I think that everybody who's here, you know, if you had phenol, all you'd have to do is take phenol and deprotonate it with a base and then treat it with ethyl iodide, and you could do a Williamson. Okay, so then the question becomes, well, can I go from here to here? Can I convert this into phenol? And the answer is yes. If you remember that when you take an aryl ether and you treat it with excess HBr and you heat it up, so if we take this and we treat it with excess HBr and we heat it up like this, we end up making phenol. No. Plus, you'd also end up with methyl bromide, but that's neither here nor there. You would purify that out of the reaction mixture. So we'll just move that down here. So now you can take the phenol and you could treat that with sodium hydride. That's going to give you the phenoxide, this. And then you treat that with your electrophile and done. Just like that. One thing I'll say about this is if you take the organic chemistry 2 wet lab, sometimes you, sorry, I lost you guys. There you are. Sometimes we do a reaction where we take a phenol and we do a Williamson ether synthesis with it. The thing is, you don't have to use sodium hydride as a base because we don't want undergraduates using sodium hydride. It's kind of dangerous. But you can actually deprotonate phenol with sodium hydroxide. So we'll put here or NaOH. And the reason that works is because the pK of phenol is so much lower than that of an alcohol like ethanol, right? If you take phenol, which has a pKa equal to 10, and you treat that with hydroxide, what's that going to give you is the phenoxide. So we'll put that here, plus H2O. So H2O has a pK of 15.7, so that means the equilibrium is going to lie to the side because, you know, water is 1,000,000 times weaker of an acid than phenol. Whereas if you were to use, you know, ethanol, all right, and then treat that with hydroxide, well, the pK of ethanol is 16 and water is 15.7, so you're going to get a whole holy host of everything. In that case, you're going to get a total mixture of the phenoxide and the you got phenoxides on the brain of the alkoxide and the hydroxide. So that wouldn't work. This wouldn't work at all. But with phenol, you can use sodium hydroxide as a base. So just putting that bug in your ear. And now for something completely different. Well, maybe not. Let's try a couple of those problems that involve reductions and then making an epoxide. So these are real classics from our textbook. We'll go over one of them, and then we'll move on to the next chapter. So this is 13.51J, and it's where you take 2-butyne, and then you want to convert that to an epoxide. So we do this. We have a methyl group coming out and a methyl group coming out here like this. And hopefully you remember that epoxidation is stereospecific. So if we have an epoxide where the two methyl groups are cis to each other, right? This is cis 2,3-dimethyl oxirane. Well, that means that we need to start with the cis alkene. So our retrosynthesis means we have to start with a cis alkene. Conversely, if you had question K, it's the same thing. You start with 2-butyne, but they want you to make the trans. So if you have one methyl group going out and one methyl group going back, like this, well, the trans has to come from a trans alkene. And so how do we reduce 2-butyne to a cis alkene, and how do we reduce it to a trans alkene? Well, these are conditions that have to be memorized. When you want to convert it to a cis alkene, you would treat it with hydrogen and Lindlar's catalyst, and that would give you the cis alkene. And then all you have to do is treat it with MCP-BA. And for the other one, if you want to reduce it to the trans alkene, could anybody remind me what the conditions are for this reaction? Bottom left.
Sodium and liquid ammonia.
Heck yeah, absolutely. All of you are 100% correct. I told you I teach the best of the best. So my students know their reactions, frontwards and backwards. And there you go. I knew you'd know the answer. MCP-BA. Perfect. There you go. Well, I think that's enough review for chapter 13. Again, if you have any questions when you're practicing, because the quiz doesn't open until Saturday and Sunday, if you have any questions, even on a Saturday, just email me and I'll do my best to answer you. Even if it's